Ladies and gentlemen, it is my pleasure in the name of the organizers of this 6-month program and in the name of the organizers of this first workshop, which is an introductory and instructional workshop, which aimed at, in particular, at researchers at an early stage in their career. So we are addressing in this workshop most of the topics which will be present within this 6 months, and some of them to greater detail, and some of them just in a sketchy way. But anyway, so without further ado, let me welcome the first speaker, and I'm very grateful to Olivier Dudas that he agreed to give this first lecture here on finite reductive groups and their irreducible characters. Please.
Thank you. Thanks, Gerhard. So it's actually a great pleasure for me to open this workshop and the whole program. So I'd like to thank the organizers of the workshop and of the program. And of course, I have a special thought for Kai, who put a lot of effort and energy in organizing this semester so we could all benefit from it. So during this week, I'll try to enjoy the workshop as he would have done by, of course, going to all the lectures, but also all the social events, with being formal or informal. All right. So I was asked to talk about finite reductive groups, which be a part of one of the themes of this workshop. So I have only 2 hours, so I decided to focus on one aspect of the theory. So I will not spend too much time on describing the structure of these groups, but I will, following the examples of the general linear group and the symplectic group, try to give you maybe a flavor of what the classification of irreducible characters are for this group. So for me, what a finite reductive group will be is just like a reductive group over a finite field, as the name suggests. So the rational points, so I'm working over finite fields, so the FQ points of a connected is important for the theory, reductive algebraic group. So G will be always an algebraic group, so an object which is a group, but also an algebraic variety with a compatible structure. But most of the time, just GLN or SP4 for the purpose of this talk. So, as I said, you can think of so this finite reductive group as being GLN over FQ, or the special linear version, projective linear group. You also have some twisted versions, like the unitary groups for the complexity groups, which I will not talk about. The symplectic groups over FQ, the orthogonal groups, and so on, up to the exceptional Lie groups. Okay, and all like combination of all these groups. All right, so the question that I want to address in these lectures is the question of understanding the representation theory in a characteristic 0 over an algebraically closed field. So for me, it would be just a field of complex numbers. So you know that most of the representation is encoded in its character in that case. So I want to understand the complex irreducible characters of this group G of F. Okay, this finite group. So by understand, what do I mean? I mean to have, for example, the labeling of the characters. That's the first step. Okay, but a natural labeling, not just any labeling. I mean, as soon as you know the number of conjugacy classes, for example, you know the number of characters, irreducible characters, and you can decide on any labeling. But this one will have to do with the parameterization of conjugacy classes, as we would see. And given that labeling, being able to tell the degree of the character, that is the dimension of the representation, and ultimately trying to be able to compute the character table of these groups. So the character values of the irreducible characters. So this was solved for GLN. Let me say just a bit of history. This was first solved for GLN over FQ by Green in 55, who showed how to construct all the irreducible characters by using some symmetric functions, and gave an algorithm to compute the character values by what we call now the Green polynomials. This was later solved for SP4 of FQ by Srinivasan in 68, I think. And for the exceptional group G2 over FQ by Chang and Ri in 74, sorry. All right. But that was before a huge breakthrough, which happened with the work of Denis, Lusztig, and Lusztig. Building from the example of this, only this example of this small rank group and GLN, they developed a whole theory using the geometry of the underlying algebraic group to show that they can answer, like, in a very satisfactory way, all these questions when the center, so any G with, let's say, connected center. So the connected center of the algebraic group G. But this uses a lot of like theory. So the main ingredients, let me just list some of them, are so the so-called Denis-Lusztig theory, also the Kashdan-Lusztig theory. So that was to construct and classify, giving a first classification of the representation into families. Then the Kashdan-Lusztig theories to understand each of these families. And then the theory of character sheaves, developed by Lusztig, to solve the problem of computing the character values. Okay, and this is 76, beginning of the 80s, and this is more recent, the end of the 80s, and still, but there's still some work going on for when the center is not connected. Okay, so, but like I have only 2 hours, and I will not talk about this thing, so not in these lectures. It's just to give you really some ideas about like the objects which are involved, and I will talk about the consequences of this work, but not really on. I mean, I'll try not to mention anything which is related to the linguistic theory in these talks. Okay, so you might be a bit disappointed, but if you want to learn more about this, I suggest to look at a few references. So the first one that I really like, but that's maybe not a book that you want to start with. It's not a book where you can from which you can learn from which you can learn from. It's Lustig's Orange Book. Okay, so you can try to open it. I remember when I was a student, so I barely knew what a group was, and I went to see Michel Brouet for advice. I wanted to know about the representation theory of finite reductive groups, and he said, "Oh, yeah, there is this book written by Lusztig. You know, it's a book. It contains everything, and it starts with very elementary stuff." So clearly, he had never opened that book, because chapter 1 is called something, if I remember well, on the computation of local intersection cohomology of some fiber bundles, line bundles on Schubert varieties, something like this. That's just a chapter 1. Okay, so it's a fantastic book once you know already some part of the theory, and if you want to understand the ideas, which are, I mean, most of them are due to Lusztig. which are behind all these theories, okay, to classify the characters and to understand the values. Okay, but a second reference, or maybe two references, which are new, which I want to advertise. So there is a second edition of a book by Dean and Michel, and a book to appear by Geck and Mahler. So if you want, so not so much is explained about casualistic theory and character sheaves in this book, but it's a fantastic book if you want to learn about finite reductive groups and understand the proofs behind everything that has to do with the linguistic theory and the linguistic characters. But if you're not really interested in the details, but you want to use the results, you should really look at this book, which is going to appear by Meinolf and Gunther, which I think is also a great book. All right. So that being said, what do I want to do in these lectures? I want to talk about, like I said, the consequences of this classification. So, and which consequences? So I want to relate. Okay, so I'm interested in the irreducible representation of this finite reductive group and the character values. So you all know that the number of irreducible characters of a finite group is the same as the number of conjugacy classes, but you should not expect a natural bijection between them unless you're in a very specific case. But here, what I want to explain is how the classification of conjugacy classes and how the geometry of these classes, so I'm talking about conjugacy classes, so how I can say FQ conjugacy classes, let's say just conjugacy classes of the algebraic group G and their topology. How the classification of these classes parallels the classification of the irreducible representation of this finite group, and how you can say something using the topology and the geometry of these classes, you can say something about the character values. But in order to do that, Denis and Lusztig realized that it was maybe better to work with not the group G itself, but the Langlands dual. So there is some kind of Langlands duality going on, which I will not explain, but I will tell you a little bit about what this group is and how it comes into the classification of these characters. All right, so really that's, I want to emphasize the fact that this correspondence really goes beyond the simple fact that if you want to understand the number, if you want to compute the number of irreducible characters, this is the same as the number of conjugacy classes. Okay. Right, so the plan of these two lectures, will be the following. Today, I will talk about the Jordan. So I've learned that I have to say Jordan and not Jordan. But it's going to be very difficult for me to say Jordan decomposition. Of both the conjugacy classes that you might know and the irreducible character of the finite reductive group. And tomorrow I will talk about a distinguished subset of the conjugacy classes here, so the unipotent classes, which correspond to unipotent or nilpotent elements in the Lie algebra. And here the counterpart for the irreducible representation, which are also called unipotent. So the unipotent characters and their values. All right. So let me start with some elementary facts on the conjugacy classes. So that would be the first part, the Jordan decomposition of classes. Okay, so and I will try, yes. So what do I need by, so I said that I want to show how this classification parallels this one. So I need to say what exactly I mean by classification and what exactly I mean by this topological data. So what I want to understand from the conjugacy classes point of view is so what we want to know. So first is a parameterization of the classes. And the classes, so you have the algebraic group G. So you have the conjugacy classes of the geometric object. It's called the geometric conjugacy classes, but also for the final group G over FQ, which I will call the rational conjugacy classes. Then we want to understand, so the first topological object that I want to understand, I'm working with a connected group. But if I look at, given any element in that group, I can look at the centralizer in G of that element. It's not necessarily connected. And the component group is actually an interesting object which plays a role in the classification. And this one I will denote it by AG of X. So for X, an element of the group. And the third topological data that I will need is the closure relation among the classes. So the relation smaller than defined by, so on classes or elements. So I will say that a class or elements is smaller than a class. So by this I mean I pick two elements X and Y and I look at the conjugacy classes. So this one is smaller than this one if and only if this class lies in the closure of this one. So I can just, it's the same as asking for the element X to lie in the closure of the class of Y. Okay, so that's a partial order that you can define on classes, and it turns out again to be very important in the classification here, especially when you want to compute the character values. All right, so I'll start with the geometric conjugacy classes. So by geometric, again, I mean, let me insist on that, I mean the classes for the algebraic group. So the orbits, the conjugacy classes for G. So let's start with GLN, a situation that probably all know very well. So in GLN, you have two kinds of elements that I would like to consider. The first kind is the semi-simple elements. So S will be semi-simple in GLN if only if is diagonalizable. Over, so in GLN, so by GLN I mean GLN over an algebraic closure of FQ if you want, so over FQ bar. Okay, so that would be a semi-simple element, just conjugate to a diagonal matrix with eigenvalues in the algebraic closure of FQ, in an algebraic closure of FQ. And the second kind of elements are the unipotent elements. So it's a group-like version of the nilpotent matrices or nilpotent elements. So U is unipotent if U minus the identity, minus 1, is nilpotent. Okay, so you can ask, so the same as requiring that U, all the eigenvalues of U are equal to 1. Of U are 1. Okay? So that's for GLN. But if I start with any connected reductive group, I can embed it into GLN, and I can define semi-simple and unipotent using the image in GLN. And the fact is that it does not depend on the embedding. So this generalizes to any G, any linear group, any reductive, so in particular any reductive group G, which you embed in GLN, in some GLN. And again, like this, the fact that it's semi-simple and unipotent really does not depend on the embedding. That's one of the first properties that you want to show when you work with this semi-simple and unipotent elements. Okay. So what do I want to do with this? Well, if I was working with GLN, or in like I'm re-looking at actual n by n matrices, if I start with an element X or matrix in GLN, I can always decompose it as a semi-simple part corresponding to the eigenvalues of X and a nilpotent part with S and N commuting. Okay? So this is like one of the instances of the Jordan decomposition. Here, since this element is invertible, the eigenvalues are non-zero, so this one will be as well. So I can factor out by S to get 1 plus S inverse N. And this is now an element U, which is unipotent. And it satisfies SU is US. Okay? So this is the Jordan, the multiplicative Jordan decomposition in GLN. And so the first theorem that I want to state, so it's for any algebraic group, it's called Jordan and Chevalet. Okay, it's not because I'm French that I want to cite two French mathematicians for this theorem. I checked on the English Wikipedia page that was called the Jordan-Chevalet decomposition. So given X, so any, X in G decomposes uniquely as X is S times U, where S is semi-simple, U is unipotent, and S and U commute. Okay. So that's for the elements. So what's the consequence on the classes? You will also get a kind of Jordan decomposition for classes. So this is what I will refer to as the Jordan correspondence, which is, if you look at the conjugacy classes of the algebraic group, starting with an element X, well, you can look at the decomposition of one representative in the class. And since you're working up to conjugacy, since the elements commute, the decomposition is unique. It amounts to consider only the conjugacy class of the semi-simple part and the conjugacy class of the unipotent part. Okay? So we can rearrange the conjugacy classes with respect to the conjugacy classes of the semi-simple part. So S stands for semi-simple here. For any S, so S being the semi-simple part, U now becomes an element which is unipotent and commutes with S. So it's a unipotent element of the centralizer of S. So I can look at the centralizer of S, the unipotent elements, and the conjugacy classes. So given a representative of one of this class, I would just send it to the class of SU, and this will give me a one-to-one correspondence. Okay? So in this way, if I just want a parametrization, I just need to understand the semi-simple classes, the centralizer of semi-simple elements, and the unipotent classes in these centralizers. Okay. So that's for the parametrization. What about the component groups here? So if I want to understand the centralizer of SU, like I said, because of this theorem, it's something that centralizes both S and U. So I can write it as the centralizer of U in the centralizer of S. Okay, so for the component group, I have the following equality. This component group of SU, it's the same as the component group for U, but inside the centralizer of S. That's the first thing. And for the closure relation, so if I have U and V, let's see, which commute with S, so let's write it SU, which is smaller than SV, the classes, for the order that I define here, which is topological, meaning that this element SU lies in the closure of the class generated by SV. I expect it to be the same if I was looking at the corresponding closure relation in that group. So U is smaller than V, but inside the centralizer of S. Okay, so somehow for me it was something that was to be expected when you want to classify the classes, but I couldn't find a reference for it. And I emailed a few people, and I could show in some particular cases, but I don't know if it's true in general. So let me just put a question mark. So of course, if U is smaller than V in the centralizer, when you saturate everything, SU will be smaller than SV, but the converse statement is not that clear. So it's maybe not obvious. But it's something to be expected. At least if you work with classical groups, this is definitely true, because you have a way to understand this relation using the various eigenspaces of the elements in the natural representation. Okay. Right. So if I'm here and I want to use this Jordan decomposition to understand the classes and to answer the three questions, or the three things that I want to understand up here. And I need to make sure that I don't leave the word of reductive groups. Okay, so when I'm looking at the centralizer of S, I want it to be a group which I can understand, which is also a reductive group. So that's the first fact. What's actually a theorem is that C G of S, if S is semi-simple, this is always a reductive algebraic group. But the only problem is that it might not be connected. So not necessarily. Reductive group. That's the first thing. And the second is, and also I want to be able to classify the semi-simple classes and to be able to compute the centralizer. This is something you can really do using the root datum and the Deakin diagram. This is probably something that Frank is going to explain in his talk. The second fact is once I've gone through this correspondence, I'm working with centralizer of semi-simple elements, but now I'm looking only at unipotent classes. So I want to be able to understand the unipotent classes. They are a component group. Okay, so the component group of SU is really the component group of some unipotent element in another reductive group, and the closure relation. And this is all known. Explicitly, and you can find like the data in some various books and also on the computer. So for these two facts, let me give you two examples. So I will need to use the projector. Thanks. All right. Okay, so let me start with the semi-simple classes of GLN. So if I have a semi-simple element, so it's just something which is diagonalizable, so it's conjugate to matrix with eigenvalues in an algebraic closure of FQ. So I've grouped them together, so Ti, so T1, T2 with multiplicity N1 and 2 and so on. Now if you want to compute the centralizer, it's a very simple exercise. You just get a product of smaller general linear groups. In that case, this is the Levy subgroup of GLN. But the situation here is very particular to GLN. That's why I want to emphasize that. For example, if you work with the projective general linear group, and even for this very elementary element, very simple element, you'll see that you get two kinds of elements which would generate the centralizer. So the torus, in which it lies, diagonal matrices, which is one-dimensional in PGL2, and this order 2 element, which, I mean, it doesn't centralize the element in GL2, but it centralizes up to multiplying by -1. So it will centralize in PGL2. And this means that the centralizer is not connected. You have the GL1 and the Z/2 acting on the top, just by taking a non-zero element to its inverse. Okay, what about the semi-simple classes of SP4? So again, you can determine them all, but I will give you just one specific example of the classes which are not good in the sense that they are not, the centralizer are not Levy subgroups. Or here everything will be connected, but it can happen that the centralizer is not a Levy. So I'll start with a Dinky diagram of type C2, like this. And I will extend it to the affine Dinky diagram. So I have now three simple roots, which is, so this is constructed by adding a node which corresponds to the opposite of the highest root in the root system. And if I do this, using this diagram, I can somehow remove the middle node, and I will get just a disconnected Dinky diagram of type A1 cross A1. And that tells me that exists, so here it would be an involution, whose centralizer would be a product of SL2, SL2 cross SL2. And this is, in that case, not a Levy subgroup of SP4. Okay, so it's important to see that, in general, centralizers of semi-simple elements can have a bad behavior. But we know how to compute them. What about the unipotent classes? So for GLN, starting with a unipotent element U, you can consider the Jordan normal form. So you have these various Jordan blocks of size λ1, λ2, and so on. And you can order, so up to conjugation, you can order them in non-increasing sequence, λ1, λ2, and so on. The only condition is that the sum, all the lambdas, they add up to n. So that gives a partition of n. And this is the classification of the unipotent classes. So for each partition, you'll get a unipotent class whose representative is this U on the top with its Jordan blocks. Okay, so for GLN, unipotent classes are parameterized by partitions of n. If you want to understand the order given by the closure relation on these classes, well, it's also something you can describe combinatorially by the dominance order on partition. If you don't know what it is, it's just like mu will dominate lambda if the sum of the first terms of lambda is smaller than the sum of the first terms of mu, like for every partial sum starting with the biggest, with the largest term. Okay, so that's for GLN. So unlike the semi-simple classes, the unipotent classes will not depend on the type of the group you consider, in the sense that they will not be affected by the fact that you're working with PGLN or SLN, as long as you look at the geometric conjugacy classes. The unipotent elements are always the same. Here they live in SLN, for example, but the centralizer, the component group, sorry, can be a little bit different. So we've seen for semi-simple elements, for GLN it was connected, but for PGLN it was disconnected. And here for the unipotent elements, that's the other extreme somehow, is that it's connected for GLN, but it would be in general disconnected for SLN. Okay, whereas the semi-simple elements, the centralizer will be connected for SLN. Okay, let me show the example of SP4. So SP4, you can see that's sitting inside GL4. GL4, you know the conjugacy classes. I've just told you that they are parameterized by partitions of 4. So you have 5 conjugacy classes. You can look at the intersection with with SP4, and it's either empty or a single conjugacy class. And here, so you start with the biggest one, which is called the regular one, which intersect non-trivially. Then you would want to look at the class corresponding to the partition 3(1), which is the one coming just after 4, and that one does not occur in SP4. So we only have the partition 2(2), so 2 square in the exponential notation, 2 1 square, and then the partition 1 to the 4, which correspond to the trivial class. You can compute the dimension of these classes from 8 to 0 for the trivial one, and the component group as well. So Z over 2 for all the classes except for the trivial one. And it's important to note for it will occur tomorrow, but that when you compute this AG of U, so it depends if you're working with SP4, if you modulate by the center, if you have a large center or not. So here I should emphasize that there's actually only one Z over 2 that's really relevant for what we're going to do, because the one for the regular class and the one for the class of dimension 4, they actually come just for the center. So if I was working with the group with connected center or trivial center, these will not occur. Okay, but the Z over 2 is an actual Z over 2 for the class of dimension 6. This one will play a role in the classification of unipotent characters. All right. Maybe, before I continue, let me just say something about, so maybe I'll give more details on the board, but so that's what I said for GLN, for the reductive group GLN, the algebraic group GLN. Now, if you want to understand the classes of GLN over FQ, you cannot force all the eigenvalues to be in FQ. They can be in some extension, but at least you know they will be permuted by Galois, the Galois action. So if I start with an element which lives in the finite group, GLN of FQ, the eigenvalues are permuted by the Frobenius. And if I want to look at now what's this centralizer of S, it's also rational. It's defined over FQ.
Lives
so
in the finite group,
GLN of FQ. The eigenvalues are permuted by the Frobenius.
FQ here.
And if I want to look at the FQ points, so the corresponding finite
this
group,
centralizer of S
group, this is
it's
not
also
a product of GLN
finite group
points over FQ. The eigenvalues are over some extensions of FQ. So you have to. And if I want to look at the count here, so the corresponding finite this centralizer of S group, this is not the length product of GLN of T1 under this action of the Frobenius. Okay, so it's only when all the eigenvalues are in FQ that this centralizer would split over FQ. All right. So yes, I don't need the beamer anymore. So yes, so let me continue with the yes. Yeah, but I'm not in control. I don't have the power. Yeah. All right. So that's that accounted for the geometric classes, the class for the algebraic group. Now let me say a few words about the rational classes. I already said something for GLN. And this is also where the component group will play a role. So it's hard to see now why I'm interested in this component group of the centralizer, but that'll become clear now and later tomorrow. So the rational classes. So for G of FQ. So for this, I'll need to introduce another way to look at this FQ points using the Frobenius endomorphism. So let me first say that something like elements, if you start with elements in GLN over FQ, which are conjugates in GLN, so FQ bar if you prefer, in the algebraic group, there are already conjugates over the final group. But it's something very specific to GLN again, and the fact that the centralizer of elements are connected. So it's not true in general. So there is something to say if you want to go from the geometric classes to the rational classes, okay? And that's given by this component group, actually, and the action of the Frobenius. So before explaining this, let me just give you one example. If I look at the matrix 1, 0, gamma 1, and the Jordan block 1, 1, 0, 1, so these two are conjugates in SL2 of FQ, if and only if gamma is a square in FQ. So you will get two conjugacy and gamma being non-zero. So for gamma non-zero, you get two conjugacy classes for the rational group, SL2, but there are conjugates in SL2 over FQ bar. So this is something that can happen in SL2 and not in GL2. Okay, so where does it come from? Let me state the main theorem. So for this, as I said, I will need to introduce the Frobenius endomorphism. So let F, so it's a morphism of algebraic groups. So it's something that was like hidden in the definition when I said I was working with an algebraic group and I was taking the FQ points, the rational points. For this, I need to be able to say how to take the points. I need to give a rational structure, an FQ structure. And this is given by a Frobenius endomorphism. So for example, if I work with GLN, and I want to have the standard GLN over FQ, I will just have to consider the coefficients of a matrix and raise everything to the cube power. And if I take the fixed point, it gives me the FQ points of my algebraic group. Okay? So here, so I want the Frobenius to be such that when I take the fixed point under F, this is the finite reductive group. Okay, this is how you can play with GLN and see that if you change a little bit the definition of the Frobenius by introducing the transpose inverse, then you'll get not the general linear group, the general unitary group over FQ squared. So why do I need this? To make the link between the rational and the geometric conjugacy classes. Let me state it as a theorem. So first of all, if I look at the geometric class, if I want to have elements in the final group, at least I need to consider only the classes which are globally stable by F. But it's actually enough. So conjugacy classes, so of the form Gx of G, contains an element of the final group. Okay? So already it's quite good because I know the conjugacy classes and I can try to see whether they are stable or not, depending on the parameters. And I know that in each class there are elements of the group. But now the question is whether these elements, so I know that there are conjugates under the algebraic group because that's the definition, it's just a single orbit. Now I want to know how many orbits for the final group I have. And this is given by the component group. So if I have now an element of the final group, and And if I look at the conjugacy classes inside, so I have this geometric orbit. I can look at all the f-stable points. So it's just the orbit intersected with the finite group. And these are parametrized by the so-called F conjugacy classes of the component group. Okay, so by F conjugacy here, I mean that I want X to be conjugate F, okay, if only if there exists G in my group in A such that AX, and not the inverse of A, but the inverse evaluated at the Frobenius equal to Y. Okay. So it's the same as saying that in the coset XF and YF are conjugate somehow. So you need to take into account the action of the Frobenius. That's important. But there is, again, a way to, for unipotent elements and for semi-simple elements, or unipotent elements, to say exactly with the parameterization how, not only what these component groups are, but also how the Frobenius act on them. All right. So that's it for the classes. So what about the characters now? I said that I want to explain how the classification of characters of the finite group. It's probably, yes, A here. Thank you. Thanks very much. Yes. Can I say it? Take a Z. Sorry. Yeah, I just wanted, for those of you who don't know about like what twisted conjugacy classes are, it's like the same as conjugacy classes, but you have like an extra endomorphism that acts when you take the inverse. That's it. And it's the same as looking at conjugacy classes, but in the coset. Something quite natural to do here if you want to take into account the action of the Frobenius endomorphism. All right, so what happens for the characters now? Of the irreducible characters. So I say that in order to understand or to make into to parallel the classification, I have to work not with the group, the algebraic group, but the dual version, the Langlands dual. So here, G star, we stand for a Langlands dual. Of G. G has some, is defined over FQ. So with the fact that G is defined over FQ, we can show that the Langlands dual as well will be defined over FQ, and the FQ structure of G and G star are related. Okay, so it's also defined over FQ. Which means I also have a corresponding finite group, the dual. And what the dual is, so it's given by exchanging the roots and the co-roots, the characters and the co-characters somehow. So for GLN, GLN is very symmetric, so you won't see anything. A Langlands dual is just GLN. But if you start with SLN, with something which a big center, you'll get the one with the triple center, PGLN. Okay? So it's a duality, so the double dual is the group. And maybe more interesting is if you start with the symplectic group, which is of type C, you end up with a root system. When you dualize, you end up with a root system of type B. So you have the spatial orthogonal group, SO, the odd-dimensional spatial orthogonal group. Okay. Now, okay, maybe I'll continue on this board first. Now, inside the conjugacy classes, I had the semi-simple classes and the unipotent classes. And the same thing happens here for the irreducible characters. I will only look at the unipotent ones. So let me just say, and I will explain how they are defined, or actually how you can define some of them tomorrow. Inside the irreducible representation, there is a set which I will denote by UCH of G of Q for unipotent characters of the group. So it's a small set of characters, irreducible characters. I won't say much about them today. I will explain tomorrow some of their properties. But let me just mention that they are, like the unipotent classes, they do not depend on Q. And also, they're insensitive to the center or the cocenter. Okay, like we saw it for the unipotent classes. I said the unipotent classes for GLN, PGLN, SLN are the same. It will be the same for the unipotent characters. So it's like a distinguished set of representation which do not depend on Q. It's really only on the algebraic group G, actually the Weil group of G, and the action of the Frobenius on that Weil group. And the theorem of Lusztig, which is a Jordan-like decomposition. So for this, I have to assume that the center is connected. So I'm doing this to ensure that the centralizer of semi-simple elements in the dual are connected. So, for example, if I start with PGLN, the dual group is SLN, and the centralizer of semi-simple elements in SLN are connected. And this is important for stating the theorem. There is a more general version for non-connected center, but that's more complicated. So let me just assume this. It's easier. So there exists a decomposition, which would be the Jordan correspondence of what? On one side, so before we had all the conjugacy classes of the algebraic group on one side, and on the other side we had, like, over all the semi-simple conjugacy classes, we had the unipotent conjugacy classes of centralizers of semi-simple elements. And here it's almost the same. I start with a semi-simple element, but of the dual group, up to conjugation, up to conjugacy. And I look at what correspond to the unipotent classes now, the unipotent characters of the centralizer of that group. So I'm working in the dual. And I consider only this distinguished set of characters. So I know that this group is a connected reductive group. When I take the FQ points, I have a proper finite reductive group. Okay? And this is a one-to-one bijection. And let me just write two character chi corresponding to an element, to a unipotent character here, and an element S. Let me just denote by chi S correspondence. So here I haven't said anything. I mean, you can have a trivial statement like this, but I need to maybe say a few properties of this decomposition. For example, if you want to compute the degree of this character with respect to this one, okay, let's say that you know in which series it lies, and you know all the unipotent characters of smaller reductive groups, and you want to understand the degrees of all irreducible characters. And this you can do because the degree, so the dimension of the corresponding representation, this is related to the degree of this smaller representation with a factor which is just the quotient of, so I have to take the dual of the p prime part, sorry, of the order of the dual group, and divided by the p prime part of the order of the centralizer. Okay, so I have some polynomial which do not involve powers of q here. So this is a of fq, sorry. So this is a subgroup of this one, and the order is actually a polynomial in q, and this polynomial divides this one. So you get a polynomial in q here, and you get rid of all the powers of q. You just have cyclotomic polynomials occurring here. Okay? And this, like this is for the Jordan decomposition of characters, but you can, for example, compare it to what was happening for the classes. If I wanted to compute the order of the length of an orbit for the finite group, if I started with an element, the orbit of an element whose Jordan decomposition is S times U, so the semi-simple part and the unipotent part commuting, then it will be just the order of G divided by the order of the centralizer of S times the length of the orbit for the centralizer. So now it's a final group, sorry. So let me put GF. Of the corresponding unipotent element. So that's some kind of, like the same kind of relation here, except that you get rid of the powers of Q which can show up. Okay, that's part of the theorem of Lusztig. You also have, so I said something about the degree, which is the value at 1, the element, the trivial element, but you also have other character values. So you cannot say directly for any character what the character value will be with respect to the character value for the small one, the unipotent character, but you can do it for what are called uniform functions, which I will not define here. But it's just to tell you, because I'll stop here with the Jordan decomposition, is that this is a very powerful tool to solve the problem of labeling the irreducible characters, computing their character degree, and also computing the character table of the group. So basically, if you know everything for the unipotent characters, then you can use this theorem of Lusztig to transfer the solution to the problem for this big group here. So that's the idea behind it. The same idea that what we did for the conjugacy classes, trying to go through the Jordan correspondence to look only at unipotent classes which are independent from Q, which you can classify, which are easier to handle from this perspective. All right, so maybe let me just say, without writing it, a few things about this correspondence. There is more to it. If I was working with GLN, centralizers of semi-simple elements are Levy subgroups. And in a case where the Levy is really defined over FQ, so you start with a semi-simple element which has all the eigenvalues in FQ, then you can have actually a functor that goes from the unipotent representation to the representation of G, which is just by some induction process from the Levy. If the centralizer is still a Levy but not defined over FQ but over some extension, there is still a way to do it using a more involved induction. This was proved by Lusztig. And maybe the stronger statement that is proved with respect to this decomposition is that if you work with modular representations, then in some cases, basically when the centralizer is a Levy, then you this bijection between characters, this is the shadow of a Morita equivalence between the category of representation. So over a field of characteristic not dividing Q. And I'll stop here this lecture. Thanks.
Thank you very much, Olivier, for this nice talk. Are there questions? Okay, so this is not the case, so